let's have a look at the next presentation, which is called More Use Cases for Simulation. And our speaker is Hardi Hungar. He is a computer scientist from the German Aerospace Center, and they're working for the Institute of Transportation Systems. He's team lead for methods and processes of verification and validation. And within the set-level project, he's the head of the sub-project 1, which is called Requirements on Simulation and its Use Cases and Demonstration Scenarios. So, Hardi, very welcome, and the screen is yours. Please take over.
So, yeah, let's look at more use cases for simulation. In the morning session, you had the chance to see one of 3 demonstrations of use cases. And in this talk, I will sketch 3 more potential use cases of simulation of what we can make use our set level results for. So first, look at have a high level view at the development process and look where simulation might contribute what. We can use it definitely for various analyses, for verifying development artifacts, for testing routines or components, or validate results, or evaluate the performance of the system. So, and here's a reminder what you might have seen in the morning. One of those 3 use cases. One was criticality identification and the hazard and risk analysis. Another one was component verification. And the third one was about closed loop analysis of system integration or system validation. Well, and in this talk, I will sketch 3 more use cases. One, again, concerning the hazard and risk analysis by mining for scenarios which are interesting. So to provide databases for this hazard and risk analysis. Second one is near to the end of the development of the automated vehicle. It's the validation of this vehicle. Once it's completely developed and one wants to look how safe it really will be on the road. So whether all your colleagues have provided sound work results. And after the vehicle has been brought to the road, still manufacturers will be forced to monitor it to look for potential flaws in the automation, and then some incidents might occur, and these have to be analyzed whether they are attributable to the automation or to circumstances not controlled by it. So these are the 3 use cases I will sketch very briefly in my 20-minute talk. First one is scenario mining. That is to look broadly for all kinds of scenarios which might occur, which are interesting for the safety of our development, that is, which might turn out critical. So how do we do that? In set level, we develop platform and simulation tools which implement the platform, which look detailedly on scenarios, but they don't really generate scenarios, but they are given scenarios. So, well, to generate all these scenarios which we might be interested in criticality analysis, we have to use some outside help. And luckily, this is available in the form of the tool Sumo, which is able to generate a broad range of scenarios by simulating traffic flows. And these traffic flows can be parameterized, dense traffic, less dense traffic, and other circumstances influencing that. And this we will couple then with a detailed analysis of what this Sumo tool has generated. Let's look at how those tools behave. We use Sumo on the left to generate all kinds of traffic situations at, say, a particular crossing, and then As you might have seen this morning in the session on the simulation use case 1, we can use OpenPath to analyze what has been generated by Sumo on this crossing and look for potential criticalities, just as Open Scenario has been proven to be able to do that in the morning demonstration. So, and fortunately, our simulation platform is flexible enough to be able to accommodate those two tools and let them interact to find critical scenarios. Here's a little sketch of how this interaction behaves. We have 3 actors. On the left, we see the simulation management, which controls everything. Then we have in the middle the Sumo tool, which does the traffic flow simulation, integrated into our platform architecture by adding a FMU, functional mockup unit wrapper. And on the right, we have OpenPath, which is already integrated in the platform architecture. And the simulation starts by letting Sumo compute traffic flows until we have a stable flow, and then the real interesting thing starts. The simulation manager tells Sumo to hand over the situation at a particular crossing, and then OpenPath takes over to simulate in detail the traffic at this crossing and does a detailed simulation, while Sumo still takes care of the rest of the traffic flow through the town. But it is not anymore responsible for the traffic on the crossing, which has been handed over to OpenPath. And once OpenPath has resolved the scenario which has been given to it and produced a verdict whether the scenario might be critical or not, then OpenPath can hand over the control of the vehicles on the crossing back to Sumo, which is then again in full control of the simulation. And the scenario which we have just studied via OpenPath in detail is then either stored if it has been interesting, that is potentially critical, or if it has been boring, well, then we can delete it. And then the same process starts over again. Sumo continues with its traffic flow simulation, and at some point in time, the simulation management says, okay, let's again have a close analysis. And in this way, by having a broad, very flexible simulation of all urban traffic, we can generate a large base of synthetic data as a basis for the further hazard and risk analysis. So that was the first additional simulation use case, and it is currently under development within Z-level. So now to the second use case. It's about evaluating how safely the end result of the development will behave on the road. If you happen to remember what we did in Pegasus with the simulation, well, that's pretty close to that. So what do we have to do to bring this step to life? So how do we set up our simulation? First, we need to define in which traffic space we will do the evaluation. That is, we need a scenario catalog of logical scenarios, which covers the specific subset of the operational driving domain, which we would like to analyze our SUT in. And then, well, we want to simulate our automated vehicle, so we better have a pretty good modeling of this vehicle, which we can feed into our simulation tools. And then, of course, we need the simulation tool itself, and it better be, for this kind of analysis, a very credible simulation tool. Remember Hans-Martin Heinkel's talk this morning about the credible simulation process, which will be instantiated here to analyze how good the simulation tool will have to be and how this is going to be proved. Well, and then these are the ingredients for our core set-level simulation. That is, we can execute single runs in our ODD. And well, with these single runs, we'll have to do our best to compute the overall risk which comes from bringing the automated vehicle into traffic. So this is a kind of elaborated procedure. Now let's look in a little bit more detail at our task, what we have to do. We would like to compute the risk. How much risk is attributed to the automated vehicle in traffic? So the risk in a particular concrete scenario is here a numerical value, and depending on the parameters of the logical scenario, each parameter combination gives a concrete scenario. For each concrete scenario, we get a risk value, and this single risk value we hope to be able to compute reliably with our simulation tool, with our credible simulation tool. Okay, this does not give us the volume yet. For that, we have to do a more extensive computation. That is, well, we would like to get the volume of the risk function graph by doing lots of single simulation runs. And this we do, well, in a way similar as Bernard Riemann once defined what is the integral of a function, that is the volume under a function graph. That is by building it up, by approximating it, making samples, in our case, sample simulation runs, which gives us single risk values, and then building columns around our single runs, our values which we have computed by simulation, and adding up the volumes of all these columns gives then an approximation of the volume of the risk function. That is an approximation of the risk we want to compute. And we do this, of course, in a, say, clever fashion. If the risk is 0 or close to 0, we don't have to look too closely because, well, this area in the scenario space will not contribute significantly to the overall risk. So we can use our sample. We can choose our sample points very sparsely there. You might have seen it on the right in the animation, where we have, say, a low density of sample points. And where it gets interesting, towards the left corner of this risk graph, we look more closely. That is, we do more simulation runs. And in this way, we get, provided we have our credible simulation tools and well-modeled SUT, we get perhaps a good estimation of the risk, of the real risk, which comes from bringing the automated vehicle into traffic. And this procedure, we developed some kind of these procedures in set level. And if you happen to know that, you might say it's something like a statistical model checking with importance sampling, which uses more or less the very same approach to do so. Okay, this is just a short glance at this interesting problem, and we will provide some support for this problem in set level. So we will not solve all of the problems which come with that. Now, I promised you a third use case of simulation, that is after production, the incident analysis. The relevant process phase is monitoring when the vehicle is on the road. And of course, as you all know, manufacturers will be forced, they will mandatorily have to look at all at the behavior of the vehicle on the road and analyze the incidents which have been observed or which are observed in this phase. And then, look for the cause of these incidents, whether they have been caused by the automation itself, by flaws in its design, or say some situations which have been not fully foreseen during the development, which are maybe not really the fault of the automation, but the automation could behave better in these cases. Then again, the manufacturer will have to argue how to cope with these situations. And at first, he has to know the cause of this incident and what can be done about it. So we need a deep analysis of all these incidents on the road, and there will be many. So to do this by simulation, support this by simulation, we proceed as follows. We first extract the scenario from the driving records, and then we make it simulatable. That is, we turn it into an open scenario, open drive description of what has gone on the road, make it into a scenario space. So to make it variable, add parameters to it. And then we analyze this concrete scenario and its vicinity, the neighborhood and neighboring parameter settings, and do this in all in a replay to sim approach to be able to find the causes for what went wrong. Okay, that is, we have 3 steps. The scenario extraction, which is mostly automatic. That is, we get these reports which are tagged by criticality values, and then we can select these reports which should be analyzed more closely. Okay, this is an automatic step. And then the next step is much more interesting. That is, make this incident report simulatable. Main problem here is to find an open drive, open scenario presentation, which is amenable to simulation, to variation of parameters, and so on. This is, I must confess, not a functionality which is in this level functionality which will be provided, but there are projects with which we cooperate, and these projects work on tools which support this step. Though I guess that some of the steps necessary to realize it will still be manual, so only partly automatic. And okay, also some research is needed to make the end result real good and a real good basis for the further analysis. Now, the analysis again will be partly automatic and in the end perhaps fully automatic. And here's again a point where you can use the end results of set level, I think, very easily, because simulating scenarios and analyzing them and evaluating them detailedly, this is just a core contribution of set level, and we will provide tools which will help you in performing this task. So that already was the 3rd additional use case I would like to present to you. And let me summarize by looking at all the use cases we see, which might support the development of an automation. In this talk, I've talked about scenario mining, that is getting a broad database to support the hazard and risk analysis, broadly generating synthetic data, which can be used then for every kind of analysis you might like to have. That is by categorizing them and making all kinds of abstractions, evaluations, and so on, the standard behavior in hazard and risk. But now you have a large database which adds to your expert knowledge and gives you reasonable assurance that you don't overlook too many in your hazard and risk analysis. The other one was the interesting problem of deep validation, very much the thing which Pegasus also thought about and developed contributions to that. And the third use case I presented was monitoring afterwards and finding explanations. We all know that in the aerospace domain, this is well, standard procedure, and also in the railway domain, and it will take up lots of resources in the automotive domain as well, of course. So, and in the morning, we've seen, or you have seen, one of three other use cases. That is, the first one was criticality identification. That is in a logical scenario space. Look for the critical instances, which is not generating scenarios, but spotting the critical ones within a scenario space, a different form of analysis, helpful for the hazard and risk analysis. The second simulation use case this morning was mainly about system integration, to look in a closed loop simulation how the system components work together, which is very close to the simulation set up for deep validation, only that for deep validation you have a different evaluation procedure and a different setup of the scenarios. And the third simulation use case was about component tests. In that case, these were sensor components which have been tested in simulation. This, of course, does not comprise all of the use cases we have or we envision for simulation and our set level results. There are lots more. For instance, during your system design phase, you might turn part of your design, for instance, your automation control strategy, into a model which you can put in a simulation to have a first check how your designed control strategy will behave, to get early feedback to improve on your design before it's going to be implemented. And during implementation, of course, you don't need much fantasy to see that there are lots of readily available use cases and for simulation, where simulation helps to test and evaluate the implementation results. And of course, there are furthermore use cases. Not all of these usages of simulation will have dedicated support by the results of our project, of course. We have limited resources after all, but some of them will. And of course, the demonstrated simulation use cases this morning will have. Well, we have something to show already, and we will improve on that. So in the end, this will be ready to use cases for simulation once you have tools and installed them in your environment, instantiated them. So you have a blueprint and you have much of the work already done. So ready to use for you. Tests and evaluations will also not pose much of a challenge, as I already mentioned. And well, we will also have some instance of this scenario mining available to get a broad data base for hazard and risk analysis. But this, well, will also need some further development for your particular application. Some other are not realized when set level as demonstrations of our tools and how they can be applied, but these are easily realized using our results. And in realizing, implementing them, you will profit from the open standard-based modular approach of our simulation platform and the implementations, which give the necessary flexibility to get into new use cases of simulations. And some other, well, will be a little bit challenging, but we hope to be able to contribute substantially to their implementation. And With this outlook, I would like to conclude my quick glance into the universe of useful applications of simulation for the development of automated vehicles. And I'll be happy to answer all questions you might have.
Yes, so thank you very much, Hardi, for this deep dive into more simulation use cases. And let's now have a look at the questions from the audience. Frank, what are the questions?
So Hardi, prepare yourself for several questions.
I am.
So the first one is maybe very simple. So why road elevation is not considered for road creation? Is it not relevant or is it not needed now? So
sorry, I don't see why road elevation is not considered here. Road elevation can be represented in OpenDrive, and well, this is the basis of our simulation tools.
Okay, so then the next one is, to my understanding, the use case scenario mining will generate valid, vastly varying scenarios on layer 4 of the 6-layer model. How could one extend this process to also mine scenarios with factors on other levels?
Yeah, that depends.
So for instance, the road infrastructure. And
that depends on how much effort you would like to put into it. Of course, Sumo is able to simulate traffic on various road networks. So network variation can enter this process by, of course, not in a single run of this co-simulation, but by altering the town in which you simulate the town layout, the road layout. You can get scenarios in other road layouts, but yes, they are not that easily varied as the moving traffic. Well, because simulation tools are more, say, developed towards varying the traffic, not towards varying the road layout that easily. So this has to be an outer loop in generating interesting scenarios, but it can be implemented. And you've perhaps seen already that there are efforts underway to make also the road network variation more easily controlled. So this could in the future perhaps enter also this kind of simulation setup, but currently, well, not.
Okay. So then a quick one, I think. So does OpenPath simulate vehicle dynamics, and is there any visualization?
Yes, it is. You might have seen this in the morning session had you picked the OpenPath demonstration. Yeah, there's a visualization, and you can make the OpenPath simulation essentially as detailed as you would like, with vehicle dynamics and weather influences and everything you would like to have. Well, depends on the model you have available.
Okay, so now maybe a more tricky one. So for deep validation, how do you distribute samples for an a priori unknown risk function?
Well, in general, it's a two-stage process. One does a quick scan of the parameter space and identifies the vast areas where there's no risk. We have risk indicators which do not jump from 0 to 1, but which indicate some slight increase of risk without a severe risk already manifesting itself. And remember that we mostly talk about physical processes here, vehicles on the road. So we do expect from very rare exceptions, that we can spot the vicinity of risks via our indicators. That is an essential ingredient. Otherwise, our risk approximation would not be really reliable. But natura non facet salta, that is, a vehicle does not jump, and an accident is indicated by close vicinity and high relative velocities and so on, these indicators. So we feel whether there might be some significant risk in the vicinity. So that's an important argument for saying that the end result is rather reliable. But that's a complicated process, yeah? And we're thinking about exploration procedures which can give you some sort of guarantee.
Okay, I have two more questions. Do we have the time to ask them?
Yes, we have time. We have until 40:30, so I think it's enough time to have two more questions.
Okay, so then the next one is, how do you know that your risk function is almost continuous? Because you applied the integral.
Yeah, essentially these are physical parameters which enter here, so they don't have real big jumps. There are changes. That is, in the end, we have a hybrid system. It's all the traffic can be modeled as a hybrid automaton, where we have discrete changes. That is, starting of maneuvers, starting of braking, and so on. But still, the end result, the trajectories of all the vehicles are continuous, though we have some discrete state changes in the controllers of the vehicles. Indeed, it is a very difficult thing to spot all these potential control states, to cover all the control states of the unknown controllers or the partly unknown controllers. A case for having these control states partly made visible for testing purposes for your automated vehicle, but it will not be complete. So this is a difficult part of it. But then what comes out of it is a continuous function, because we live in the physical world.
So then the next one, how do you get from trajectory-based scenario recordings to good modifiable neighborhood scenarios? This is, I think, also an answer where you need some more words, I think.
This is, I guess, concerns the incident analysis. Indeed, this is an interesting problem and not solved yet. So you can get, so there, again, I can refer back to Pegasus. There have been approaches to that in extracting from, say, data recorded on the street, a maneuver-based representation of what went on the street. Imagine that open scenario will have maneuvers which enable the adequate representation of everything which goes on the street. Then the only thing we have to do is to identify these maneuvers once they have their concrete instances and the concrete incident record. This will be not completely correct on first guess and in first implementations, but this is more or less a thing which I think, given enough effort and development time, can be solved adequately, or say in a way on which we can base these results, these analyses which we want to conduct. Needn't be the correct maneuver which captures in a most adequate and precise way what went on the street, but it only has to, say, cover what went on the street and not in the best possible way. And I think this is not a thing which cannot be done, but it requires effort. World of maneuvers is finite in the end.
Okay, so then there are two additional commands or questions regarding, I think, the continuous risk function. So one is physical objects might spot up very sudden, and the other is with more an explanation and pointed out occlusion is an example where you may have very sudden pop-up of an object.
Yeah, this gets really complicated then, numerically complicated to get good approximations. There are steep inclines of risk functions. I agree to that. They are not too common, but these are the interesting parts, and you need an elaborate procedure which tries to say bound these steep inclines and to get a good boundaries on the risk, compute good boundaries on the risk there. This will be a challenge, and I cannot say I have the solution to that. I have ideas for the solution. There's a publication on that, but still in the concept phase and being implemented, and one has to try and see how well the result will be. I guess I would bet on it. It can be controlled, even these steep inclines, but not in the first attempt. Yeah, this will require again some development work and some scientific ground laying for that. But don't be afraid of that. Problems are there to be solved there, aren't they?
Okay, so yeah, I think this is a good some good last words, and we can close the Q&A session. Thank you, Hardi, for answering all the questions. I think you are young enough to do some further research on this for the next decades. So really looking forward for the next findings. Okay.
Okay, so thank you very much again, Hardi, for the detailed answers of the questions. And Frank, thank you very much for managing our Q&A sessions. This was very helpful.
Thanks for the interesting question formulation, Frank.
Yes.